Welcome to Embedded Microprocessors. My name is Dr. Rick McDaniel, and I will be your instructor for this course. I'm excited to guide you as we explore the world of microprocessor-based control systems and their applications in industry. In this course, we will concentrate on the Allen-Bradley Programmable Logic Controller, PLC. Allen-Bradley PLCs are among the most widely used industrial controllers worldwide, and developing skills with them will give you a strong foundation for work in automation, robotics, and mechatronics. By the end of this course, you should be able to understand the role of microprocessors and PLCs in modern industrial control systems. Identify the major components of a PLC. Write, edit, and troubleshoot programs using relay ladder logic. Apply timers, counters, and data handling instructions to real-world problems. Develop confidence in reading wiring diagrams and designing control logic. Let's get started. This first chapter sets the stage by introducing what PLCs are, why they are used, and how they compare to traditional control methods. By the end of this lecture, you should understand not only what a PLC does, but also why it has become the backbone of modern industrial automation. PLCs are the most widely used industrial process control technology in the world today. Whether it's an assembly line, a packaging system, or a water treatment plant, chances are a PLC is running the show. A PLC's primary job is to control machines and processes. Think of it as the decision maker that responds to sensors and tells motors, valves, or lights what to do. Instead of a human constantly monitoring, the PLC executes the logic automatically, 24/7. At its core, a PLC is a computer, but one specifically engineered for industrial environments: dusty factories, hot conditions, vibrations, electrical noise. PLCs connect to the real world through inputs and outputs. Inputs are the devices that send information into the PLC. Things like sensors that detect temperature or pressure, push buttons that an operator might press, or limit switches that tell the system when a machine has reached a certain position. These are the PLC's way of seeing what's happening in the process. Outputs are the devices that the PLC controls, the actions it takes in response to those inputs. That includes motors to drive conveyors or mixers, lights to signal operators, or solenoid valves to open and close fluid or air lines. In other words, inputs tell the PLC what's happening, and outputs are how the PLC makes things happen. This makes the PLC the bridge between the digital logic and physical machines. The way we tell the PLC what to do is through a control programming language, most often relay ladder logic. This programming style was chosen because it looked familiar to electricians and engineers who were used to relay diagrams. Next, we'll look at why PLCs replaced the older relay logic systems and what advantages they brought to industry. PLCs were originally created to replace relay logic systems. Before PLCs, control panels were filled with dozens or even hundreds of mechanical relays, wired together to perform logic operations. These relay panels worked, but they were bulky, slow, hard to modify, and prone to mechanical failure. With a PLC, all those relay functions could be programmed in software instead of wired in hardware. This not only saved space, but also made the system easier to troubleshoot and update. If you want to change the control logic, you simply rewrite the program instead of rewiring the entire panel. On the right, you see an old-style relay. That's what PLCs replaced. On the left, you see a compact PLC. Notice how much smaller and cleaner it is, and yet it can do far more than a cabinet full of relays ever could. So, the PLC didn't just replace relays. It revolutionized how we control machines. Next, let's look at why PLCs are more reliable, flexible, and cost-effective compared to relay logic. On the left, you see a traditional relay control panel. Notice the large number of wires, relays, and connections. Each relay represents a single logic function. To build a complex control sequence, you had to physically wire many relays together. This made panels bulky, expensive, and difficult to troubleshoot when something went wrong. On the right is a PLC-based control panel. Notice how much cleaner and smaller it is. Most of the logic has been moved from hardwired relays into the PLC's program. Instead of rewiring to change logic, you just update the PLC program. The key advantage here is that a PLC eliminates much of the hardwiring required in relay systems. Fewer wires means less chance of wiring errors, reduced maintenance, and faster troubleshooting. Next, we'll look at other advantages. In traditional relay systems, every function depended on hardwiring. The more wires and relays, the higher the chance of a wiring mistake. If one wire was misplaced or a connection failed, the entire system might not function as intended. With a PLC, the control logic is stored in the program memory. This eliminates wiring errors in the control logic itself, because the program instructions take the place of dozens or even hundreds of physical relay connections. Once programmed, the PLC runs the same way every time, with no risk of a miswired relay or a loose terminal causing logic faults. This is especially important in high-volume production, where reliability means less downtime and more consistent output. Imagine trying to wire a panel with 50 relays. Even if it works today, vibrations, dust, or maintenance might cause wiring faults later. With a PLC, those 50 relay functions are all replaced by lines of software code stored in memory. Far less to go wrong. This reliability is one of the main reasons PLCs are trusted in mission-critical industries like automotive, chemical processing, and energy. Next, we'll examine how PLCs are more flexible. With relay-based control, every change to the system required physically rewiring circuits. That meant pulling wires, adding relays, and sometimes redesigning the whole panel, a slow, expensive process. With a PLC, the logic lives in the program, not in the wiring. If you want to change how the system works, you don't have to rewire. You just modify the ladder logic program. This makes it much easier to test, update, and improve a system. On the bottom, you see typical inputs: a push button, a limit switch, a sensor. On the top, you see typical outputs: a contactor, a light, a solenoid valve. The PLC sits in the middle. Instead of wiring all these devices together through relays, the PLC connects them through simple input-output terminals, and the control sequence is handled in software. Imagine a packaging line where you decide later that you want the conveyor to stop after 50 boxes instead of 100. With a relay system, that's a big change, rewiring and adding counters. With a PLC, it's just a few keystrokes to change the count in the program. This flexibility is one of the biggest reasons PLCs became the standard. They allow engineers to adapt quickly without tearing apart the hardware. Every relay you add to a control panel increases cost. Not just the relay itself, but also the wiring, terminals, and labor to install it. Once you start needing more than a half dozen relays, the expense adds up fast. A PLC can replace dozens or even hundreds of relays with one device. The upfront cost of the PLC is quickly offset by savings in wiring, hardware, and installation labor. This is why, in most industrial applications, a PLC ends up being the cheaper option in the long run. Maintenance costs are also lower with PLCs. No worn-out relay contacts, fewer wiring faults, and easier troubleshooting. Changing the system doesn't require new relays or rewiring, just updating the program. The image here shows a panel full of relays. Imagine the cost of buying, wiring, and maintaining all of this. Now imagine replacing it with a single PLC and a neat set of I/O connections. Far less expensive and far more efficient. So PLCs aren't just more reliable and flexible. They're also cost-saving once your system grows beyond a few relays. Next, we'll look at the communications capabilities of PLCs. Modern industrial systems rarely use just one PLC. Instead, multiple PLCs often work together, each controlling part of a process. To coordinate, they need to communicate with each other and with higher-level computers. A communications module allows a PLC to connect to a network, similar to how your computer connects to the internet. The diagram shows PLCs and computers connected to a local area network. This allows data to flow between control systems, operator stations, and higher-level enterprise software. For example, A PLC might send production data to a central computer for logging or receive set points from a supervisory system. In a factory, one PLC may be controlling the conveyor, another controlling the robot arm, and another monitoring sensors. Communication ensures they work together in sync. Next, we'll look at why speed also matters when PLCs are controlling processes in real time. In many industries, machines process thousands of items per second, like bottles on a conveyor line or parts in an automated sorter. When products only spend a fraction of a second in front of a sensor, the controller must react almost instantly. PLCs are designed with extremely fast scan cycles. They can detect an input, process the logic, and activate an output in milliseconds. This speed makes them ideal for high-throughput environments where even a small delay could mean defective products or wasted materials. In the picture, sensors are detecting bottles as they pass on the conveyor. If the PLC didn't react quickly, it might miss a bottle or fail to activate the filler or capper at the right moment. Because the PLC responds so fast, every single bottle can be detected, filled, capped, and labeled at high speed. So far, we've seen that PLCs are reliable, flexible, cost-effective, and now, very fast. Next, let's talk about how they're also easier to troubleshoot and test compared to relay-based systems. With relay panels, troubleshooting meant physically tracing wires, testing relays, and hunting down mechanical faults. This was time-consuming and often required taking the system offline for extended periods. PLCs make troubleshooting easier because you can watch the program run in real time on a monitor. Inputs and outputs are highlighted as the logic executes, showing exactly which part of the program is active. This helps technicians quickly see why a motor didn't start or why a sensor didn't trigger the right response. With older relay systems, testing a field device like a push button or limit switch meant tracing wires all the way to the device, often using a multimeter to check continuity. This was time-consuming, and fault could easily be missed if wiring ran across large panels or factory floors. With a PLC, all field devices are connected to common input and output terminals. This makes it possible to test multiple devices directly at the control panel without hunting through the wiring. For example, if a push button isn't responding, the technician can check its input status right at the PLC's input terminal or in the software monitoring screen. In the next lecture, we will examine the individual parts of a PLC.